Welcome back to another Regents physics review. This one is for modern physics. I've taken multiple choice entry response from the last two Regents exams because there's not typically a ton of modern physics questions on the exam in the first place. It should cover everything in that unit. So let's get into our first example. Alright, so example number 1 here. We have which particles exhibit properties of waves in some experiments. So my particles here are going to be the photon and the electron. So you have the photon. A photon is a pocket of light. So we have what photons are. They either really act as a wave or a particle. That's how we kind of figured out. Some people said that light was just a wave. Some people said that light was a particle. Wave-particle duality shows that it is going to be both, because you have just things that make light a wave, which is like diffraction, or it shows that it could be a particle by being able to bounce off and reflect off of things. Or when you look at the photoelectric effect, when you shoot photons at a metal, electrons can be excited off of that metal, and you can actually see it based on like an electroscope. If you had a good enough UV light, you could see this with an electroscope, and you can actually have the electroscope leaves kind of move away from each other because the electrons have left the electroscope. And you can look that up on YouTube. There are videos of that. So the photon can be both a wave and a particle. So a photon would be an answer choice to this one. And now you're looking at your electron. So electron can act as a particle, obviously, but it also can act as a wave. So if you think about the double slit experiment, I showed that video of Quantum Man. I think it was the CGI guy with the like showing the waves and diffraction through the slits. An electron does behave as both a particle and a wave, dependent on the situation you had there. If you weren't observing the electrons go through the slits, it kind of made a wave pattern, but once you put an observer next to it, all of a sudden it acted like a particle again. So the electron and the photon can act as a wave or a particle at any point. So we have here that it can exhibit a property of a wave. So answer choice 3, both photons and electrons, is going to be my answer. So let's move into example number 2. Moving into example number 2, we have a nuclear reactor produces 2.7 times 10 to the 16th joules of energy per year. How much mass is converted to energy by the reactor in 1 year? So whenever you have a question like this and has to deal with energy converted to mass or vice versa, it's always going to be E equals mc squared. This is the only energy equation that doesn't involve either. When we go back to say, or in this unit you have energy of the photon. It's not saying anything about a photon here. Going back to energy earlier in the year, you have kinetic energy or potential energy. It doesn't say anything about something moving. It doesn't say anything about a height. And whenever you have conversion of matter or conversion of energy straight into matter, that is a mass energy equivalence, and that is E equals mc squared. So looking at this equation, what am I given here in this question that will lead me to this? So what I have here, the first thing is I have that the nuclear reactor produces 2.7 times 10 to the 16th joules of energy per year. So I have my energy is 2.7 times 10 to the 16th, and that is going to be joules. In this equation for mass energy equivalence, I have C, which is the speed of light in a vacuum. Again, you don't have to memorize this at all. If you go to the front page of your reference table, and you look there towards the very top, you'll find speed of light in a vacuum, and it is 3.00 times 10 to the 8th, or I just like to write it out as 3 times 10 to the 8th meters per second. All right, and we are trying to find mass. That is going to be m. So that is my question mark. So with this, I'm going to do the algebra first, like we've been doing since it's good practice for the free response questions, and then we will solve for my mass. So looking at the equation here, we have E equals mc squared. Mass is attached to c squared by multiplication, so I'm going to divide out from each side. So let me write it out again over here. So E equals mc squared. I have c squared that is attached to my mass by multiplication. I want the mass by itself on the right side since that's what I'm solving for. So I'll divide out c squared from both sides of the equation. And I end up with the energy over c squared equals my mass. So now we're just going to plug in to the equation and into our calculator and end up with the answer. We have our energy on top, 2.7 times 10 to the 16th joules. On the bottom, I have 3 times 10 to the 8th meters per second. Make sure to put parentheses around that and square that value. That is equal to my mass. So now all I'm going to do is plug this into my calculator. So 2.7 times 10 to the 16th. Divide that by 3 times 10 to the 8th squared. So I should end up with 0.3, and that mass is going to be in kilograms. So 0.3 kilograms is equal to my mass, and that is going to be answer choice number 1. So the hardest it can get with this type of question is if they say change joules into like gigajoules or megajoules or something like that. This is possibly like the easiest version of an E equals mc squared question. Doesn't get much more difficult besides them playing around with the units in certain ways. So let's move into our next example. All right, so moving into example number 3, we have an anti-muon neutrino is A. All right, so what I put on the slide here is the bottom of page 3 of the reference table. Again, the reference table is in the description down below if for some reason you do not have it. But we're going to be referring to this in a few of the questions, so I'm just going to put it next to it just for ease of what I'm talking about. So with this, I have 4 answer choices. Answer choice 1, lepton with a -1 elementary charge. Answer choice 2 is a lepton with 0 charge. Answer choice 3, a meson with -1 elementary charge. And then answer choice 4, a meson with 0 charge. Alright, so I'm looking for anti-muon neutrino. What I can see on the reference table, if I look here at the particles of the standard model, I can find the muon neutrino if I circle this here. Find a muon neutrino. That is going to be a charge of 0, but it's telling me that we have an anti-muon neutrino. So what's an anti-particle? It says right directly below that note for each particle, there is a corresponding anti-particle with a charge opposite that of its associated particle. So for 0, opposite of 0 is going to be 0. So it's going to stay with 0 charge, and you can see here that we have a lepton. So we're going to end up having answer choice 2, a lepton with 0 charge. It's not a meson. A meson is just a quark and an anti-quark, so both those answers can go away. So if you want to like know an idea behind an anti-particle, like one that actually becomes a different charge, look up here above muon neutrino. You just have a muon that is -1 elementary charge. So the anti of that would be +1 elementary charge. But for this one, since we have 0 charge to begin with, the anti of that is going to be 0. So our answer here is a lepton with 0 charge. So let's move into our next example. All right, so example number 4. A deuteron is formed by combining a proton and a neutron. So the mass of a deuteron, I think I'm saying that correctly, is 2.3 2.39 times 10 to the negative third universal mass unit less than the combined masses of a proton and a neutron. This mass difference is equivalent to, so all my answers here are in mega electron volts. So you might be thinking I'd do some crazy conversion here. But actually, if you look on the front page of the reference table for universal mass units, it does exist on here for just a fairly quick conversion. It says at the very bottom that one universal mass unit, U, is going to be 9.31 times 10 to the second mega electron volts. So I want to get myself into mega electron volts. So this is essentially just a kind of longly worded conversion because I have my mass here. So I'm going to write this out. The mass is 2.39 times 10 to the negative third universal mass unit. So I can do this conversion straight from a universal mass unit into energy because again on the reference table it tells me what one universal mass unit is in mega electron volts. So this is a conversion here. So I'm going to write out my mass again. So 2.39 times 10 to the negative third. Oops. And you have here U for universal mass unit. All I want to do is get rid of this unit. So I'm going to put 1U on the bottom. And I'm going to put my conversion factor on the top, which is going to be 9.31 times 10 to the second mega electron volts. So I fix this 9 so it doesn't look like a 4. So then all you're going to do is plug this into your calculator and end up with the answer because my universal mass unit is going to cancel and I'll be left in mega electron volts. So just plug this into your calculator, 2.39 times 10 to the negative third multiplied by 9.31 times 10 to the second. And you should get around 2.23. So 2.225, so 2.23 mega electron volts is going to be the energy here, or the difference, or the mass energy is equivalent to this energy. So that is going to be answer choice 2, 2.23 mega electron volts. And again, this is just a glorified conversion. If you end up with something that says universal mass units, you just go to the front page of the reference table and convert into mega electron volts. So moving into my next example. All right, so example number 5, we have a meson could be composed of a top quark and a bottom quark, 2, an electron and an anti-electron, 3, a strange quark and an anti-charm quark, and 4, an up quark and a muon. So again, I've brought out this part of the reference table. This is the third page in the reference table. If you don't have a reference table, again, it is in the description down below. It is very important for modern physics. A lot of the answers will come from either this or the energy level diagram above this in the reference table. For this one, it says that we have a meson. So looking at my classification of matter, I have here hadrons and leptons. Leptons is pretty much a dead end, so we don't go further with that. Going further with hadrons, you have the baryon and the meson. It tells me here that the meson is going to be a quark and an anti-quark. So all I have to do with these answers is look for one that is a quark and an anti-quark. So we're going to be up here in quarks. So don't worry about leptons. So again, anti-particle is just a particle that is corresponding to the original one. It is just a different charge, essentially. So we have here answer choice 1, a top quark and a bottom quark. That is not going to be an anti-quark. Those are both just regular quarks, so that's not going to be an answer. Answer choice 2, an electron and an anti-electron. Again, those are leptons, so that is not going to be an answer. Answer choice 3, a strange quark and anti-charm quark. So looking at my table here, a strange quark would be this here. And then an anti-charm would be the one above it, just with the opposite charge of now negative 2/3 E instead of positive 2/3 E. And since that gives us a quark with the strange and an anti-quark with the anti-charm, that is going to be my answer. So answer choice 3 is the correct response for this question. Number 4, you have there an up quark and a muon. You're not going to combine a quark and a lepton, so that is completely wrong. So again, answer choice 3 is my proper answer. But I'm given a regular quark, and I'm given an anti-quark. And that is what a meson is based on the classification of matter on the reference table. So let's move in to our next example. So example number 6. We have an electron in an excited mercury atom is in energy level G. What is the minimum energy required to ionize this atom? So with this, when you have energy levels, again, your reference table is very important in this unit. If you do not have one, it is in the description down below. And I put it on the slide for this one as well. So the first thing with this, with energy levels, again, page 3 of the reference table, directly above all of the classification of matter and the standard model, you have the energy level diagrams. There are two atoms that we work with, either hydrogen or mercury. For this situation, we are working with mercury, so we're going to circle this one. The difference between the two is mercury works with letters for the levels, obviously besides their differences as atoms. If you look at the two diagrams, mercury works with letters for my levels, whereas hydrogen works with numbers for the levels. So that should kind of tip you off as well if you're in the wrong place and you're looking at hydrogen for some reason and you're looking for G. Just know that you're supposed to be at mercury. That's where all the letters are going to be. So with this, all I want to do now is look for energy level G, and I see it right here. There could be a little bit of difficulty with this reading off what the actual number is, but that's pretty much the most difficult thing that it ends up happening with these. You have a little bit later on, the part 2 on last year's exam was a full question with this where you get the energy in electron volts, you make conversions, and you figure out what type of color it ends up being. So that's like the deepest they get into those questions. This one is a fairly simple version of an energy level question. So what I gotta do is read across the diagram now from G, and you see that it goes up a little bit here. And it connects with negative 2.48 electron volts. So then all you want to do is go from G to ionization, which is level J. So essentially looking for the difference there in the energy. Since level J is 0, all I'm doing is just negative 2.48. That's the energy I will then need to get to ionization. So 2.48 electron volts is going to be my answer because G, that's where I'm at, 2.48 or negative 2.48 electron volts. To go upwards, I am then absorbing the 2.48 electron volts in order to get to ionization. So my answer is answer choice 3, 2.48 electron volts. So let's move into my next example. So example number 7. Two muons would have a combined charge of. So again, I have my standard particle table out here. This is on the 3rd page of the reference table. I'm going to look for what two muons have in charge. And then it seems like they're all in coulombs, so I'm going to have to make a conversion because on the reference table, they're in elementary charges. This goes all the way back to electrostatics. Making those conversions at the very beginning of electricity from elementary charges into coulombs. So look at this. We have here what a muon is. Look under leptons. We are given this as a muon is negative 1 elementary charge. So now all I have to do with 2 muons is convert this into coulombs. So looking on the reference table here, so I have, again, -2 elementary charge is going to be my charge. Now I just want to get this into coulombs, so charge is Q. This equals -2 elementary charges, and I want to get this into coulombs. So if I look at the reference table, I can find that 1 elementary charge E is 1.6 times 10 to the -19th coulombs. This is again on the front page of the reference table. So if I want to go from elementary charges into coulombs, I'm going to cancel out the elementary charge. So I will put 1 elementary charge on the bottom. On top, I will put 1.6 times 10 to the -19th coulombs. And with this, all I have to do is now multiply it in my calculator. My elementary charges will cancel out, so now I'll be back into coulombs. So then you have -2 times 1.6 times 10 to the -19th coulombs. Just plug this into your calculator real quick, and you will end up with the answer. And yes, the negative is important, as you can see based on the answer choices. So plugging this into my calculator, I'm going to end up with an answer here of 3.2, or -3.2, times 10 to the -19th coulombs. So that is going to be answer choice 1. You could also use the conversion reference table for 1 coulomb. It would be the same thing. It would just be a little bit of a bigger number there on the bottom. So I would recommend doing the 1.6 times 10 to the -19th. That one's a little bit of an easier conversion for this situation. So let's move into my next example. All right, so example number 8, where the lambda baryon has the quark composition UDS. Which particle has the same electric charge as the lambda baryon? All right, so first off, we gotta see what UDS actually is in charge, and then figure out which of these particles has the same charge as that. So looking at this here, what is up on the reference table? You have here U, that means it is up. If you look up here, you have the letter U. So that charge there is positive 2/3 E. So my U, that's positive 2/3 E. Then we have D, which is going to be down. That is directly below up. That is going to be -1/3 E. And again, this is on your reference table on page 3. The next one here we have is S. That is going to be directly next to down, and that is strange. That is also the same charge here as down. That is -1/3 E. Alright, so if I add these all together, I have positive 2/3 minus 1/3 minus 1/3. That's essentially positive 2/3 minus 2/3. That is going to give me a total charge here of 0, or 0 E. So I'm going to be neutral, essentially. I don't have a positive, I don't have negative, I am just a neutral particle. So then looking at my 4 answer choices, which one of those is neutral? I have the neutron, that is obviously neutral. Electron is not neutral, so that is not going to be my answer. Same thing with my proton. And then answer choice 4, anti-muon. On here, you have the muon is -1 E, so that is not going to be my answer either. So the neutral particle, that is the same as UDS, is going to be my neutron. That is going to be answer choice 1 for this question. So let's move into my next example. So example number 9. How many kilograms of matter would have to be converted into energy to produce 24 megajoules of energy? So I was talking about earlier about how they can get a little bit fancy with E equals mc squared. It's like the hardest it probably gets for this question because you have to make a conversion of the energy in order to get it back into joules now. So with this again, how do I know this is going to be E equals mc squared? We have kilograms of matter would be converted straight into energy. So it's not saying anything about a mass moving. It's not saying anything about a mass at a height. It's not saying anything about an energy of a photon or anything like that. It's just saying straight mass into energy or matter into energy. So that's how I know that is my mass energy equivalence. That is going to be E equals mc squared. All right, so my energy here, it's going to be 24 megajoules. That is big MJ. Obviously, we know that C is going to be 3 times 10 to the 8th meters per second. That is on the front page of the reference table. But I'm not going to write that down quite yet because I want to make my conversion. So how do I go from megajoules into joules? So this is actually on the front page of the reference table, whether you see it right away or not. It's with the prefixes for the powers of 10. So joules is my normal unit for energy. So what this essentially tells me on the reference table, based on mega here at the very top, 10 to the 6th, this is essentially telling me that for 1 megajoule, it's the same thing for any unit like this, that 1 megajoule is going to be 1 times 10 to the 6th joules. This would be the same thing, say, if you had a mega meter or something like that. It would be telling me that 1 mega meter would be 1 times 10 to the 6th meters or something like that. A good version of this is, say, grams into kilograms. You see on the reference table that kilo is 10 to the 3rd. So grams into kilograms, I have 1 kilogram is 1,000 or 1 times 10 to the 3rd grams. So that's a simple conversion for my prefixes for powers of 10. That's how I make those conversions. So now all I have to do is get this into joules. So I'm going to have 24 megajoules times basically 10 to the 6th. So 24 times 1 times 10 to the 6th. That is going to give me, I'm going to give it to you in scientific notation. So give me a moment with my calculator. That is going to give me 2.4 times 10 to the 7th joules. Again, if you don't know your scientific notation, what's going to end up giving you in the calculator here is 2, 4, and then 1, 2, 3, 4, 5, 6 zeros. So in total, 8 numerals, you would then minus 1. That's how I get 2.4 times 10 to the 7th. Or in your calculator, you should be able to go to mode, and you should see there next to normal is SCI. On these regular scientific calculators, it should be the normal is flow, and you can also do scientific. If you then use your answer and plug it back in, you can get straight away in scientific notation. That's how it's going to give me 2.4 times 10 to the 7th joules. So now all I have to do is use my equation to get my answer here. We again know that C, straight from the front page of the reference table, is 3 times 10 to the 8th meters per second. So let's again use our equation, solve for what we have to solve for algebraically first, and then plug in. So we have here that energy is equal to mass times the speed of light squared. Mass is connected to the speed of light squared by multiplication, so I'm going to do the opposite and divide this out from both sides of the equation, and I will have that my energy over the speed of light squared is equal to the mass. So all I'm going to do is plug in what I have here. So I have that the energy in the proper SI unit, 2.4 times 10 to the 7th joules over my speed of light, which is 3 times 10 to the 8th meters per second. That is all raised to the second power is equal to my mass. So again, all you gotta do is plug this into your calculator now and get your answer. So you should end up here with, so you have 2.4 times 10 to the 7th, 3 times 10 to the 8th raised to the second power. Just divide those two numbers then, and you're going to end up with your answer here of 2.67 or 2.67. That's the answer that they're giving me up there. 2.67 times 10 to the negative 10th, and kilograms is going to be my unit. So looking at my answer choices there, I should end up with answer choice 2, 2.67 times 10 to the negative 10th kilograms. So let's move into our next example. So example number 10, where a red photon in the bright line spectrum of hydrogen gas has an energy of 3.02 times 10 to the negative 19th joule. What energy level transition does the electron in a hydrogen atom undergo to produce this photon? Okay, so there's a lot here, but I'm given energy and it's saying we're producing a photon, so I'm given an energy of a photon essentially. And on my energy level diagram, because it's giving me energy levels, I have this in electron volts. But in the question, we are being given this in joules. So again, my energy here, and this is the energy of a photon, is going to be 3.02 times 10 to the negative 19th joules. All right, again, on my energy level diagram on the third page of the reference table, I am given all of my energy in electron volts. So having it in joules right now is not going to actually help me all that much. I'm going to need to convert from joules into electron volts. So if I look on the reference table on the front page, I'm given here somewhere what 1 electron volt is in joules. So again here, I have my energy is 3.02 times 10 to the negative 19th joules times, on the front page of the reference table, I'm given that 1 electron volt is 1.6 times 10 to the negative 19th joules. I'm going to put joules on the bottom because I want to cancel it out. So 1.6 times 10 to the negative 19th joules is 1 electron volt. So again, this will give me my units then in electron volts when I make this conversion. So just plug this into your calculator and you should end up with the energy of the photon now in electron volts. So 3.02 times 10 to the negative 19th. Divide that by 1.6. 1.6 times 10 to the negative 19th. And you're going to end up with my energy in electron volts as 1.89 electron volts. All right, so now all I do is look at my answer choices and see which one of them is going to produce a energy of 1.89 electron volts. So looking at my reference table, what equation is this going to end up being? The equation that ends up working with my energy level diagram is going to be that the energy of a photon is equal to my energy initial minus my energy final. So all I'm going to do with each of these answer choices is do this equation and see which one of them is going to line up with 1.89 electron volts. So let's look at answer choice 1 here. So we have the equation. So we're looking for energy of a photon. This is equal to my energy level initial. So looking at the reference table on page 3, we are working with a hydrogen atom. So we're looking here, the first answer choice gives me energy level 3. So energy level 3 gives me an energy initial of negative 1.51 electron volts. That is going to be minus a then at energy level 2, that is going to be negative 3.4 electron volts. So then just doing here, keep change. I'm going to plug this into my calculator. So negative 1.51 plus 3.4 is going to give me an answer for my energy of the photon. That is then going to be equal to 1.89 electron volts. So that's going to line up with the energy that I was given here in the question. So my answer here is going to be answer choice 1. From level n equals 3 to level n equals 2. I don't have to do any of the other answers here to end up verifying this. This is the first answer choice. They kind of made it nice for you with this question. So let's move into my next example. All right, so example number 11. This is the free response from last year's Regents. What we have here is 4 parts, or essentially what's going to be 5 questions on the Regents, because you have 5 points available to you here. I'm going to do this in multiple slides, just so everything doesn't get crammed on one. So we'll do part A and part B on this slide, and do part C and D on the next, and that will be shown in the chapters of the video. So we have here that a mercury atom emits a photon when an electron in the atom moves from energy level F to energy level D. So part A, we're determining the energy of the emitted photon in electron volts. So part A here. What is the equation that has to do with energy levels and emitted photons, or the energy of that photon? If you look at the reference table in modern physics, you have 2 sets of equations for energy of the photon. You have there first the wave-particle duality, one with Planck's constant, hf and hc over lambda. What you have directly below that is the equation that we need for energy level diagrams, which is energy level initial minus energy level final. So plugging this in here, we have E of the photon is going to be EI minus EF. So we're going to use this equation and the energy level diagram in the reference table to get my answer for part A. So you don't have to write out the equation here all the way because it's not a show your work question, but I would recommend it here because it is good to just get in the habit of doing all of the equations and making sure you know where you went wrong if you did make a mistake. So with this, going to your reference table, it tells me that we have a mercury atom, so I'm going to work on the mercury side of the energy level diagrams. And we have here my energy level initial, which is F. Looking on there, if I find F on mercury and I go all the way across, the energy that goes with that is going to be negative 2.68 electron volts. And then the energy that is going to go with energy level D, if I look on the reference table again, I look for D, I go straight across, and I have there negative 4.95, so minus negative 4.95 electron volts. So all I'm going to do is plug this into my calculator, keep change, and get my answer here for part A, the energy of the photon. And that is going to be, so negative 2.68 plus 4.95. That is going to be my energy of the photon in electron volts is 2.27 electron volts. And if you forgot that the energy is supposed to be in electron volts, even though they tell it to you in the question, for these type of questions on the Regents, they'll give you a line with the actual units. All you have to do is put in the proper number here. So 2.27 electron volts is going to be your answer. So now we're going to figure out what this energy is in joules, so part B. So this is my conversion from electron volts into joules. So again, we're going to go to the front page of the reference table and figure out what this conversion is going to be. So I'm looking here, I have my energy, that is 2.27 electron volts. I now want to get into joules. So this conversion in the reference table, it tells me that 1 electron volt EV is 1.6 times 10 to the negative 19th joules. So I'll put my electron volts on the bottom because I want to cancel out that unit. And I will put 1.6 times 10 to the negative 19th joules on top. And this will now be my conversion. So I have here 2.27 multiplied by 1.6 times 10 to the negative 19th joules. And I will then end up with an answer as 3.63 times 10 to the negative 19th joules, and that is going to be my energy of the photon in joules. So those are my answers for part A and B. I'll bring this over now into part C on the next slide. So let's move into parts C and D. All right, so part C, we're going to now calculate the frequency of the emitted photon. So there is an equation that involves frequency and the energy of the photon on the reference table. This equation is going to be energy of a photon is equal to Planck's constant h times the frequency f. So now let's see what we have here from the previous parts that are going to help us in this question. We have here my energy of the photon in joules. That's what you want for this equation. That's why we made that conversion. The energy of the photon in joules, so E photon. We got in part B as 3.63 times 10 to the negative 19th joules. We also then have H. That is going to be Planck's constant. Again, this is something on the front page of the reference table, so you don't have to memorize this at all. You look for Planck's constant on the left side of the reference table. You see that this is H. And on the right side, you have the actual number for it. This is going to be 6.63 times 10 to the negative 34th. And that is going to be joules times seconds. All right, so with this, what I'm going to do with my equation here is do the algebra first and then end up with plugging in my numbers because that will get me the points for the Regents. So I have here energy of a photon is going to be equal to h times f. I want my frequency of this photon. Frequency is attached to Planck's constant by multiplication. So do the opposite here and divide out h from both sides. So I should have energy of the photon. Oops. Over Planck's constant is equal to my frequency, which then now I just have to plug in my numbers. So energy of the photon, that is 3.63 3.63 times 10 to the negative 19th joules over Planck's constant, which is 6.63 times 10 to the negative 34th and joules times seconds. That is equal to my frequency. So now all I'm going to do is plug this into my calculator, and I should end up with my answer. So this all here is my first point, writing out the equation, and then putting in the substitution there with my proper units. So plug this into your calculator now. So 3.63 times 10 to the negative 19th divided by 6.63 times 10 to the negative 34th. And you should end up with a frequency here of 5.48 times 10 to the 14th. And the unit for this is hertz. If you forget that, that is on the reference table with the electromagnetic spectrum. And that is my answer there for my frequency. So that is part C. So now part D is just essentially looking at the reference table with my frequency under the electromagnetic spectrum. That's why it says determine the classification on the electromagnetic spectrum, and to end up with your answer from there. So I have 5.48 times 10 to the 14th hertz. So on the electromagnetic spectrum times 10 to the 14th, that is either going to be under infrared or visible light. Since we have a number here that is going to be above the first visible light, which is red, we are going to be in visible light. So looking in visible light now, all you're going to do is find where 5.48 times 10 to the 14th lies. So it's going to lie in between the two numbers there for each color. So the first one again here, red, 3.84 times 10 to the 14th to 4.82 times 10 to the 14th. It's not going to lie in there. So I move over to orange. That's 4.82 to 5.03. It's not going to lie within there. Looking at yellow, 5.03 to 5.2. It's not going to lie in there. If I go to green, that is starting at 5.2 and goes to 6.1. That is going to be where 5.48 is going to lie. Again, this is the second page of the reference table. The electromagnetic spectrum is going to lie in green. So green is going to be my answer there for part D. Alright, so that is all of the questions from modern physics for the last 2 years, for the last 2 tests actually, because we didn't have a test from 2020 and 2021. So you can see that there's not a lot of questions on modern physics for the Regents. Last year there was 5, including this one, so there was 4 multiple choice, and the one part 2 of the free response. The year before that there were 6 multiple choice questions. I would study this anyways because these are pretty good points if you can get them. A lot of it is just being able to look at the reference table, and the equations are not too bad. Alright, so I hope this was helpful for everyone who's been able to watch it. See you guys on the day of the Regents, and good luck in studying for your Regents.